This is Chapter 18, Section 2, dealing with resistors in series and in parallel. And our next lab we have, you'll get to play around with resistors, different kinds of resistors, both in series and parallel. So if you've got a series circuit, it's where you have two or more components of a circuit that provide a single path for current. And resistors in series carry the same current. So if you're talking about a single path, this would be like my one individual circle, from start to finish off your battery that you've got. If you do have resistors in series, then they will carry the same current. And if you have an equivalent resistance, it can be used to find current. And there is the formula. So equivalent resistance equals the resistance of your first resistor plus the resistance of the second plus the resistance of the third, and so on. So this is if you have resistors in a series circuit. So you can write down that bottom equation there, right there, to fall back on later. Looking at resistors in series, what are our two resistors here? What is it implying?
The light bulbs?
It's the light bulbs themselves. So it's the filament within the light bulb that's your actual resistor. So instead of them, they're showing two resistors there. They could have added the little circles like a light bulb if they wanted to. If you go back to our schematic drawings, it did look like a resistor with a circle around it to show that it was a light bulb. Notice you have two resistors that are in a single path, so it looks like one complete circle, and that is considered to be series. This right here, if you've got two or more resistors in your circuit that have the same effect on the current, it will have, if they do, it equals one equivalent resistor. And what was our equation for equivalent resistance?
The sum of all.
Right, sum of all of them. So R1 plus R2 plus R3, and it just keeps going on. And they have rewritten your equation for current. What does I stand for?
Current.
Current. What about delta V?
Voltage. Change in voltage.
Potential difference.
Potential difference. And then it's over equivalent resistance. But again, equivalent resistance would be a calculation of its own before you could plug it into this equation. So again, multiple resistors set up in a series circuit, that's how you calculate current. So we have a sample problem. You have a 9-volt battery connected to 4 light bulbs. Find the equivalent resistance for the circuit and current in the circuit. You can probably do that in your head. What's the equivalent resistance? You've got 2, 4, 5, and 7 ohm resistors. What's the equivalent resistance?
9 times 4.
No.
18.
18. So 2 plus 4 plus 5 plus 7 is the equivalent resistance. And now it's asking you to find current also. So how would you find current?
Divide that by 9. I mean, take 9 and divide by 18. Because delta V is on top, and then the resistance is on the bottom. So
I don't know why they go through all of this stuff. Whew. So there's equivalent resistance, and then I equals delta V over R, the 9-volt battery, just like she said. Divide the two, and you get a half an amp is your current. A half an amp. Pretty easy calculations, right?
wow, half of this chapter was just like that sample problem.
Yeah, that was, I don't know why they went through all that, but they sure did. I have it marked out, and I should just delete those slides.
Probably.
Okay, it tells you to evaluate it for resistors connected in series. The equivalent resistance should be greater than the largest resistance, and it was. Let's see here. Series circuits require all elements to conduct electricity. You're going to find out that that bullet point is going to be different when we get to parallel circuits. So every resistor in your series circuit, everything has to actually conduct electricity. So as seen below, it says a burned out filament in a string of bulbs has the same effect as an open switch. So because the circuit is no longer complete, there is no current. Your Christmas lights, especially older Christmas lights, very common for your string of lights to be set up on a series circuit, meaning you had one wire that connected every single bulb. So if you had one bulb go out for whatever reason, the entire string wouldn't work. Most of our Christmas lights nowadays are set up with a parallel circuit. So if you have one bulb go out, it might just be a certain section goes out, but not the entire string. Let's go look at this video.
Resistors may be connected in series or in parallel or in some combination of the two. The relationships between the total current, total voltage, and total or equivalent resistance are different for series and parallel configurations. The behavior of streams of water can be compared to the behavior of electric current in series and parallel circuits. In series circuits, the current is the same everywhere, like a stream running past a series of rocks. However, if the rocks sit in a stream, the water flow splits to move between the rocks, like current in a parallel circuit. The change in potential energy of water flowing downhill can be compared to electrical potential differences. Water running down a series of steps, like current running through resistors in series, loses some potential energy at each step. However, if a waterfall is split by a series of stones, each stream has the same distance to fall, and so the change in potential is the same for each stream. Ohm's law can then be used to show how resistances behave in series and parallel circuits. In series circuits, because voltages are additive, so are the resistances. In parallel circuits, however, because the currents are additive, the reciprocals of the resistances are additive.
Okay, so lots of things on this last slide. They were kind of trying to put all of it together. Some things that you do need to write down in your notes. Make sure that you have. Starting off with a series circuit, it tells you that your voltage is additive. So you've got that one there. So V1 plus V2, and that just keeps going on. Your I times R, what's I times R?
V.
It's V, which is Ohm's law that you've got right there at the top. But you can see it is also additive. If you want to see your potential difference, basically you add up all of your potential differences at R1, R2, R3, and so on. And then also resistance. We've already looked at that in a series circuit. Your resistance is additive. So depending on how many resistors you have in your series circuit, you would add up all of those. Then we look at the parallel circuit. That's what we've got there at the bottom. You do have some differences there, but your current, your total current, it tells you it is additive. So I1 plus I2 plus whatever other currents you might have. V over R, which is your current. So that's V total voltage, total potential difference over each of your resistors. You can see how it's additive. And then your resistance itself, it's really the reciprocal of the resistance that is additive. What do I mean by reciprocal?
The opposite.
Okay?
Inverse.
So inverse, or you flip your numbers there. So 1 over your total resistance, then you add up the reciprocals, 1 over R1 plus 1 over R2, and so on. That's if you're dealing with a parallel circuit. And we will talk, starting on the next slide, the specifics about parallel circuits and how they're different from your series circuits.
Wait, what's the difference between, like, what's important about a parallel circuit?
We're gonna get to it.
It's
I mean, you can.
inverse.
Well, you can see what the difference is, like the first three that you have for your series circuits, how everything is additive there. And at the bottom, everything's additive, but whenever you're talking about V over R or 1 over R, it's always the reciprocal.
Gotcha.
So calculations are going to be just a little bit different. Moving on to resistors in parallel. This is where you have an arrangement, describes two or more components of a circuit that provide separate conducting paths. One of the examples in the video, how did they separate their path?
Rocks.
With rocks. Okay, for current, because the components are connected across common points or junctions. So it's giving you an example here. Lights wired in parallel have more than one path for current to travel. Parallel circuits do not require all elements to conduct. Do we have just one complete circle there?
No.
No. We have lots of circles that are going on. So lots of different paths you could look at. So you could have where you just conduct in, say, the circle here. I mean, I could just keep changing it up. Or maybe this circle right here. Maybe just the far circle there. Or you can have multiple circles that are conducting electricity at the same time. So this is how you want your Christmas lights to be set up. They still don't do an individual path for every light the way this shows, but it's going to be smaller groupings instead of just one path for the entire strand. So any questions on how you set up resistors in parallel? Because like I said, you'll end up having to do this in your next lab.
When is that going to be?
Maybe next week.
Next week. Oh, wait, when?
There's an example of two light bulbs set up in parallel. Again, you can see that you actually have multiple paths for your current to travel. What if I wanted to find resistance, total resistance? How would I find total resistance for that one?
Add up R and R2.
No. Remember we talked about reciprocals?
Yes.
So 1 over the total resistance is 1 over R1 plus 1 over R2. So it's still additive, but you're looking at reciprocals there. So for resistors in parallel, they have the same potential difference across them. Same potential difference across them. Here's what that means. If I have two light bulbs set up in parallel, each light bulb is going to have the same brightness. But if I have two light bulbs set up in series, they won't have the same brightness. They will both be a little dimmer than if they were by themselves. So for your Christmas lights, if they were all set up in series, expect the light bulb brightness to be dimmer as you go down through it. But in parallel, we want everything to be the same brightness. The sum of the currents in parallel equals the total current. We did look at that. So that was like I total equals I1 plus I2 plus keep on going. So that's not the reciprocal. Whereas equivalent resistance, if you're looking at it, you are looking at the reciprocals before you add them. You ready for a sample problem?
Sure. Am I?
Okay. So we have a 9-volt battery connected to 4 resistors, 7 ohms, 5 ohms, 4 ohms, 2 ohms. So it's the same light bulb, same battery that were set up in series earlier. Now we have them set up in parallel. And they want you to find equivalent resistance, which is Req, and current, which is I. So do y'all want to see if you can't calculate these to get the same answer?
Yes.
See if you can't find Req. So if we're looking at this right here, you get down to the point where you find 1 over REQ equals, what did it equal? 1.09? It was this right up here. So 1.09 ohms. No, that's not the symbol. How would you get REQ by itself? Like, you didn't have a reciprocal button on your calculator. How would you get it by itself?
You could set up like a portion and put 1.09 over 1.
Okay.
And you do 1 times 1, and you get 1, and then you divide that by 1.09.
Okay. So if I'm looking at it right here, bring REQ over to the other side, and we do what with it?
Put it over 1.
Well, you've got 1 over REQ equals 1.09 ohms.
Sorry.
Are you laughing at my symbol?
No.
Okay. So bring REQ to the other side. That is 1 equals 1.09 times REQ. And then divide both sides by 1.09. And your final answer was?
0.9814.
0.917.
0.917 ohms?
Yes.
Okay. 0.917
That
ohms.
seems to be what the PowerPoint got.
Yep. I just want to make sure you can do the math. Now you got to go figure out the current. What was the current?
That's what I'm at. 0.98.
So take our 9-volt battery, divide it by the equivalent resistance, 9.8 amps. So do you see with the same light bulbs, the same battery, how the current is different from if you have it in series versus if you have it in parallel?
Right.
Yep.
Oh, that's it for today.
When I first looked at this, it was like 30 sides.
Yeah.
Yes. But it's a lot there.
Okay. We've got one more thing to look at. This right here, talking about evaluating, it says for resistors connected in parallel, your equivalent resistance should be less than the smallest resistance. Wasn't it just the opposite for series?
Yes.
Yeah, but it's
Yep.
because it's the reciprocal.
It is. And that would be why. This right here, resistors in series or parallel. Schematic diagrams, which we've looked at. So in series, you have one path for current. In parallel, you can have multiple paths. It shows you your current, how you do your calculations. For series, notice your current is equal for every resistor. It's not an additive process, but it is an additive process for parallel. For potential difference, notice current and potential difference, they're just the opposite as far as how you calculate. Do you see that? So for parallel, now it becomes additive, but for potential difference in series, sorry, I said that backwards. For potential difference in series, it's additive. For parallel, they're equal to each other. And then you're having to deal with a reciprocal when you talk about equivalent resistance of a parallel circuit. Okay, any questions?